In the previous video, we went through a magnet with the north side down that was moving towards the loop. Now let's really quickly go through the opposite scenario where the magnet is being pulled away from the loop. We see that the external magnetic field is down at the surface. And again, the surface we're interested in is inside the loop. So we would say that our flux through the loop is decreasing. Because the flux is decreasing, our induced magnetic field needs to be in the same direction. So notice that our induced field is now also down. So we use the right-hand rule to actually figure out what way the current's going. And again, you want to curl your fingers in the direction that the current is going to then have your thumb align with the induced field, so we get this clockwise current. What's worth noting is that this is the opposite direction of how the current was induced when this was being pushed towards the loop, and that does agree with some of the experiments that we began this chapter with. So again, keep practicing this until all of the steps make sense. I want to briefly go through some of the possibilities here. And this picture is of course in the book, and if you want to really stop and study this, feel free to pause the video and do that. But briefly, we can think about the magnetic field being up or down, and then we can think about the magnetic field strength increasing or decreasing. If you have a steady magnetic field, meaning that you don't have a change in magnetic field, then you have no induced current, right? So please, this is a place where students make a lot of mistakes. If you have a steady current, if you have a steady magnetic field, if your flux is not changing, there's no induced current. So then notice, in the case where both of these fields are increasing, your induced magnetic field is shown in a dashed line, and it's opposite. So if your magnetic field is increasing, your induced field is going to be opposite. It opposes the change. And then you would use your right-hand rule to get the current. And notice that your current's in opposite directions from one another, which makes sense since your induced magnetic field is in opposite directions. On the other hand, if your magnetic field is decreasing, your induced field always goes in the same direction. Again, in this case, those fields are opposite directions, so your current is opposite. So these are roughly the possibilities. Now, we will talk a little bit later that there can be some other scenarios where you get induced current due to the area changing or the angle changing, and you'd still think about flux. But this is a good start when you're just thinking about the magnetic field itself changing. So one more example that I want to run through. In this case, you have an upper loop and a lower loop, right? So the upper loop is the one that has a battery in it and a switch. Remember that the switch is the key ingredient because our current creates our magnetic field, and the magnetic field has to be changing. So we're only going to see an induced current when the switch opens or closes. So this upper loop is creating the magnetic field, which impacts our lower loop. We are going to do the situation where the switch is opening. So if you think about the switch opening, that means your current is decreasing. It is going to zero, but we're going to call that decreasing. That means your magnetic field is decreasing. And in both of these cases, I'm talking about the top loop. So the first thing we need to do is get our magnetic field direction, okay? And notice that this is a dipole loop. Now, I struggle a little bit with these kind of pseudo 3D views. You might want to do a top view, you might want to do a side view, but when I use my right-hand rule to have my fingers go in the direction of the current here, my thumb points up. That tells me the direction on the inside. And remember that we would kind of have these circly things happening here, right? So we kind of know that I have circles, down, it's like that. So if I try to sketch this out a little bit, we see that what's going to happen at that lower loop, right, imagine some really big circles here, is that at the lower loop, my magnetic field is up, okay? So my magnetic field is up at the lower loop, and we see that it is decreasing in magnitude. So my induced magnetic field must also be in the up direction, And so if I color that red, sorry to switch colors, my induced magnetic field opposes the change. Since the change was a decrease, it's in the same direction as the original one. And then you say, okay, right-hand rule, what do I have to do to create that? Well, a current in this direction creates that induced field. So then we figure out what current we would get based on this switch opening. This is the figure from the book that solves the problem, finding the exact same thing, but using fewer pretty colors. Again, using the right-hand rule, you figure out the field from the upper loop, which is the same direction as the lower loop. You then say, since your magnetic field is decreasing due to the switch opening, your current dropping, basically becoming zero almost instantaneously, then your induced magnetic field is also up. Your right-hand rule gives you that current, and it's actually the same. So please, again, think about this in 4 steps. It's really important you always figure out what the change is. The book keeps italicizing that because it's really easy to just start thinking about absolute what was the magnetic field, but you always have to think about the change. So hopefully this has helped. Again, there are some more examples in the book. Try to practice through it and go back and review the steps that were covered in the previous video.